Hello, welcome to this video on kinetics, reaction kinetics, and Mohi asked for this, so let's do what we can. Now, first of all, I think it's important that you know where the equations come from, the rate equations come from. Okay, so what I'm going to do first of all is very quickly go for where we get these. Okay, as we all know, they form this kind of general form, don't they? R is K into AB. All right, and we have an M there and an N there. This thing is called the rate. This thing is called the rate constant. This and this are the concentrations. Concentrations of A and B. And these are the exponents to which the concentrations are raised. So these are known as the orders. Okay, so in this particular equation, M is the order of reactant A. So it is M order with respect to reactant A. N is the order of reactant B. So it is N with respect to reactant B. And the overall order of the reaction is equal to M plus N. Okay. Now, I think it's important where you understand where the rate equation comes from. So I'm going to spend hopefully not too long on this. If this lasts too long, I'll quit this one and start another. I'll start another video. All right. So let's have a look at an equation. All right. Let's have a look. I'm going to say A plus B gives C plus D. And we want to know how this reaction is affected by different changes in concentrations of A and B. Okay, I want to put this this equation into a mathematical form. So I want to see how the concentration of A affects the reaction. I also want to know how the concentration of B affects the rate of the reaction. And then I want to put it into a formula called the rate equation. All right, now the only way to do this is by experiment. That's very important. The only way we can find these rate equations is by experiments. Only way. It must be experimental. All right, so how am I going to do? Experiment one. I'm going to change concentration of A. Okay, and I'm going to leave concentration of B as constant. Okay, how do we keep the concentration of B as constant? Well, we use what we call in chemistry a large excess. In other words, there's so much B around that even if some gets used up, effectively the concentration remains the same. Okay. Now, as the reaction proceeds, then the concentration of A is going to decrease, isn't it? As A is used up, but the concentration of B is going to stay the same because it's constant because we're using a large excess. So if I were to graph this, I'd get something like this. Okay, that's reasonably good. All right, and I'm going to put on the left, this is the concentration of A in moles per decimeter cubed. And across the bottom here, I'm going to put time. Now, the reaction starts off here. Let's, for argument's sake, call it 1 mole per decimeter cubed. And therefore, this is 0.5, and this is 0. As the reaction proceeds, the concentration of A will decrease because it's a reagent. The only reason the concentration of B does not decrease is because we're using a large excess. Okay, and that's important. We only want to change one thing at once. All right, so if I plotted this graph, I would, hopefully you'd all know this, the reaction would look something like that. It would go down like that. In other words, the concentration of A would decrease with time as it gets used up. Okay, so this graph here was made by experiment. That's the only way. All right. Now what we do is we can take some. There's a nice one, but let me change that around. We can take some. Whoopsie daisy, that's not what I wanted at all. We can take some readings on this. We can take the gradients and find the rate at that time. So let's find the rate right at the start there. Let me use a different color. I'm going to use this color, purple. Okay, I'm going to use a gradient right there, right at the start. Okay, that's one gradient. I've done it again. Okay, now I'm going to pick another gradient somewhere in the middle. Let's say there. Okay, there's a gradient there. And then I'm going to pick a third gradient. Oh, done it again. All right, and I'm going to pick it somewhere near the bottom, down here somewhere. Okay, obviously my graph's not great, is it? But there you go. Okay, I picked 3 gradients there. All right, get rid of that. All right, now this one, first one is at 1. All right, the second one, second gradient is about 0.5, isn't it? It's about there. And the third one is about here. I'm going to say pretend this is 0.1. Okay, so first of all, I did my graph of concentration against time, and I had to do that using an experiment. But then I found 3 gradients on that graph. Okay, and so now, if you look at it, what are the gradients here? Well, if you imagine the first one, let me draw it over here. Let me pretend this is the first one. Okay, this is the one at 1. This is this one. All right, now if we find the tangent of this line, all right, it is rise over run, isn't it, or something like that. So it's this quantity over this quantity. So the tangent, or the gradient, same thing, is x divided by y. X is in moles per decimeter cubed. Y is in seconds. Okay, so the tangent gives us moles per decimeter cubed per second, which is another way of saying it gives us the rate. So if I find the tangents at 3 points here, I find the rates at 3 points. Okay, so I found the rates I found it at concentration 1. Oh, why am I putting square brackets on that? I have no idea. I found it at concentration 1. I found it at concentration 0.5. And I found it at concentration 0.1. Now, using those rates, I'm going to draw another graph. And this is my second graph. Now, this graph is going to be rate. These are the gradients I found from this graph up here. Rate, and the rate is going to have units moles per decimeter cubed per second. And I'm going to do it against concentration. Okay. Now, and the concentration is in moles per decimeter cubed. Now, as you remember, I took 3. I took one at 1. So one of them, I'm going to get a point here. This is concentration 1. I did one at 0.5, about here, and I did one at 0.1. Okay. Now, as you can see, at concentration 1, this one here, the gradient is steepest. So I'm going to get a rate that is greatest here. Let me get a different color. I'm going to get a rate up here somewhere, because at concentration 1, the rate was the greatest. At concentration 0.5, the rate was a little bit less. So I'm going to pretend it's down here. And at concentration 0.1, this last one, the rate was at its lowest. So I'm going to pretend it's about there. Okay, and now I'm going to get a ruler again and draw a nice curve, or draw a line, sorry, as best I can. It's not great. That's not so bad, is it? There we go. Okay, there's my gradient. Oh, sorry, there's my graph. I'm making a graph of these. Oops, daisy. There we go. Okay, and I find a nice straight line there. Okay, oops, this is going to be too big. All right, there we are. All right, and now, obviously, I have a straight line graph. This is straight line, and it goes through the origin. Okay, so a graph like this is known as a proportionality graph. There's a proportionality present. Proportionality. Okay, and now what does that mean? It means, looking at this, the rate, this thing here, is directly proportional to the concentration. And if you remember, I should have mentioned this earlier, but it's the concentration of A, isn't it? So rate is proportional to the concentration of A. It's not proportional to the concentration of A squared, it's proportional to the concentration of A. So we can say then R, the rate, is equal to some constant. I'm going to call this K1 times the concentration of A to the power of 1. Okay, so from this we can say that the rate is order 1, or first order, with respect to concentration of A. So if I double the concentration of A, the rate will double. If I halve the concentration of A, the rate will halve. But this is only under a very specific situation. This is only if we keep the concentration of B constant. Okay, this holds only if we keep B constant. Okay, so we can say the rate is some reaction constant, some rate constant, times the concentration of A if concentration of B is kept constant. All right, so we're halfway there, but we're not all there yet. So we have to do everything again. Okay, and now let's rewrite again. I apologize if I'm repeating myself, but I think this is some nice maths here. So A plus B, so B gives C plus D. All right, and now we're going to keep the concentration of A constant. We're going to do exactly the same as we did before, and we're going to vary the concentration of B. Okay, we're going to change the concentration of B. So let me draw another graph after I've done this. Okay, there we go. We draw another graph, and this is concentration of B now. This is going to change. Again, I'm going to start at 1. There's 0.5, and let's say 0.1 again. All right, and I'm going to do this against time in seconds. Okay, and again, I should get a graph that looks something like this. Okay, again, I'm going to do it quickly. Oops, I need a different color. I need a tangent here to find the rate there. Tangent here to find the rate there. And the tangent down here somewhere to find the rate there. So I'm doing exactly the same with B as I did with A. Okay, and now, you know what I'm going to do now? I'm going to plot this graph again. Okay, so this graph will look like this. And on the left, it's going to be rate. And down here, it's going to be concentration of B. Okay, and let's pretend I get this point here. Let me do a different color. This is 0.1. This is 0.5. And this is 1. Okay, exactly the same as I did before. Okay, different color maybe. And now I get this, there, there, and there. Okay, now I join these together. Let me get a nice color, blue. That's awful, so let me get rid of that. I wish I could do this better. All right. Now this is not a straight line. Okay, it's not. So we're finished here, aren't we? This is not a straight line. So what we can deduce from this, the rate proportional to B is not true because we don't get a straight line. So now, well, this is what physicists and chemists do when we have this situation. We draw another graph, and instead of plotting rate against the concentration of B, we plot rate against the concentration of B squared and see what happens. Okay, and if I do that, we get that, that, and that. Okay, I join these lines together. I get a straight line if I do rate proportional to the concentration of B squared. So now we can guess this. The rate is proportional not to B, but to B squared. If I do my maths, I get rate is equal to some reaction constant times B, concentration of B squared. And I'm going to call this K2. Okay, so this is the rate equation only in one specific situation. This is only true if the concentration of A is kept constant. Okay, so we have, if you remember, from changing A, is when we changed A, we got rate is equal to K1 times A. Okay, and then the second one we did it with B, changing B, we got rate is equal to K2 times B squared. This is sort of only works when B is kept constant, and this only works when A is kept constant. But I can combine these two to get a general form. Okay, now I'll get a new rate, and let's do this in a new color. Let's do this in green. If I combine these, I get k1 times k2 into a b squared. Okay, now k1 is a constant, k2 is a constant, a constant times a constant is a third constant, and I'm going to call that just big K. Okay, so therefore the overall rate equation for this reaction, rate is equal to big K times the concentration of A, concentration of B squared. That's how we formulate a rate equation. Okay, I think it's very, very worthwhile knowing that personally. Okay, now let's have a look. So with respect to reactant A, it is first order. With respect to reactant B, it is second order. But overall, it is an order 3 reaction, or third order. Okay, because 1 plus 2 is equal to 3. Okay, now the constant, the units of rate is always moles per decimeter cubed per time unit, but I'm going to say per second. The concentration unit is moles per decimeter cubed, and therefore the unit of K is going to vary. It's going to vary. If I have, in a third order reaction, for example, the unit of K is different to what it would be for a second order reaction. All right, now that's how we made the rate equation. I'm going to stop this video now, and I'm going to continue this with part 2.